Hello everyone, myself Pranjal Sharma. It is a continuation of my previous topic, units and measurement. In today's video, we will learn about on dimensional analysis. So, before going to discuss on this topic, I have a suggestion for the new viewers that I have made videos on several videos on units and measurements. Please watch them, then you will understand this video properly. Okay, now in my first lecture on units and measurement, I have explained different system of units and where I have also told about SI system. SI system, under which I have explained 7 base quantities. And with the help of these 7 base quantities, we can express any other quantities. So those quantities which can be expressed with the help of the 7 base quantities, those are known as derived quantities. Now, what are the 7 base quantities? These are mass, length, time, temperature, electric current, amount of substance, and luminous intensity. And their units are, for mass it is kilogram, for length it is meter, for time it is second, for temperature it's Kelvin, for electric current it's ampere, for amount of substance it is mole, and luminous intensity is candela. And these 7 base quantities are considered as 7 dimensions of physical world, and they can be denoted as, for mass, dimensions, for mass it is m, for length it is L, for time it is T, for temperature it is K, for electric current it is A, for amount of substance it is mole, for luminous intensity it is CD. So in this way we can express 7 dimensions of physical world, and every physical quantities, every derived quantities can be expressed in terms of these 7 dimensions. With the help of these 7 dimensions, we can express any physical quantity. So, dimension of a physical quantity is nothing but how can we express that physical quantity in terms of these 7 dimensions of physical world. Okay. I have explained the SI system and these base quantities and its units and its definitions all are explained in my first video on units and measurement. Please watch it. Then you will understand all these things properly. Now, how can we express a physical quantity in terms of its dimensions? Suppose I want to express speed in terms of dimensions. Speed is nothing but distance by time. Distance means length. So for distance means length, so its dimension should be L. For time it is T. So dimension of speed equal to L T inverse. Suppose I want to calculate momentum, dimension of momentum. So momentum is mass into velocity. So dimension of mass, dimension of velocity, and dimension of speed is similar to dimension of velocity. Okay, so for mass, the dimension of mass is m. For velocity, the dimension of velocity is lt inverse. So dimension of momentum is m l t inverse. Suppose I want to calculate dimension of force. So before going to dimension of force, we need to derive another dimension known as acceleration. Acceleration is nothing but rate of change of velocity. So dimension of velocity divided by dimension of time. So velocity is nothing but lt inverse, and it is time here. So the dimension of acceleration is L T inverse of 2. Now we can express dimension of force. Dimension of force equal to mass, dimension of mass into dimension of acceleration. So dimension of mass is m, dimension of acceleration is L T inverse of 2. So dimension of force is m L T inverse of 2. In this way we can calculate dimension of physical quantities. I have shown you how we can calculate dimensions of different physical quantities. Now we have found that we can express force as m L T inverse of 2, or speed as L T inverse, or acceleration as L T inverse of 2. So these are in the form of equation. So these are known as this type of equations are known as dimensional equations. Dimensional equations. Okay. So why we need to study dimensional analysis? Through using dimensional representation, we can check the consistency of any physical equation. Suppose you have derived any physical equations which can explain certain physical phenomena. To check whether this equation is correct or not, the first preliminary test is to check the dimensional consistency. What it means? Actually, we cannot add two physical quantities with different dimensions. We can add speed with speed, speed with speed, or force with force, or momentum with momentum. But we cannot add speed with force, because these two quantities have different dimensions. So we can add or subtract two physical quantities only if both the physical quantities have same dimensions. This principle is known as principle of homogeneity. Principle of homogeneity. Principle of homogeneity. To check any physical equations, we have to check whether that particular equation obey the principle of homogeneity or not. Suppose we want to check the consistency of dimensional consistency of a physical equation. Let S equal to ut plus half of at square. It is a simple kinematic equation where S is known as displacement or distance, U is velocity, T is time, A is acceleration. Here, right hand side of this equation, that is right hand side, and this is left hand side, must be equal dimensionally. Must be equal dimensionally. Dimensionally, must be equal dimensionally. That means the dimension of left hand side, that is S is displacement, so its dimension is length. If I want to calculate the dimensions of right hand side, so there exists two terms. One is U and T. So for U is a velocity or speed, so its dimension is LT inverse, and for T it is for time, so it is simply L T inverse of 1 plus 1, so it is simply L, and half of AT square. Here half is a dimensionless quantity, so A is acceleration. Its dimensional formula is LT inverse of 2, and this is T square. So again L, so this is T minus of 2 plus of 2, so it is simply again L. So dimension of S is L, ut is L, and half of AT square is also L. So these three are these three terms have same dimension, so this equation obey principle of homogeneity. Now let's check another equation. Suppose half of mv square equal to mgh is another equation. We have to check its dimensional consistency. So right hand side is equal to m g h, dimension of m, g and h, where m is the mass, g is the acceleration due to gravity, and h is the height. So m is dimension formula is capital M. G, it is acceleration. So I have already derived the dimension formula acceleration, which is L T inverse of 2. H is nothing but height, so it is length. So dimension formula here M L into L square T inverse of 2. Now check the right hand side, left hand side. For left hand side, here again half is dimensionless quantity. Dimension of M, dimension of V square. So dimension of M is capital M. Dimension of V, L T inverse. V is here speed or velocity. This is speed or velocity. Velocity. M is mass. So again M L square T inverse of 2. So right hand side is equal to left hand side. So this equation is dimensionally correct. Dimensionally correct. So any physical equation which can explain any physical phenomena only when if that particular equation obey the principle of homogeneity, that means that particular equation must be dimensionally correct. Now we will learn how to deduce an equation by using different physical dimensions. Let's consider the case of simple pendulum. Simple pendulum. So here the length is L, length of the string is L, and the mass of the bob is M. The acceleration due to gravity is in this case G. The time period of the pendulum is depends on three parameters: length, acceleration due to gravity, and mass. So we have assumed that the time period of the pendulum is depends on these three parameters. Let's see how we can calculate the time period expression in terms of L, G and M, that is length, acceleration due to gravity and mass, with the help of dimensional analysis. Let's check it. So in that case we have considered that the time period can be expressed as K L to the power X, G to the power Y and M to the power Z. That means here K is a dimensionless quantity, dimensionless constant. Okay. L, G and M have certain powers. Now in right hand side we express them in terms of dimensional formula. So T equal to, here K is the dimensionless quantity, so it will not appear in the dimensional formula. So now L to the power x, z to the power y, m to the power z. So T, we know that time plot T, so its dimensional formula is T, and L dimensional formula is L to the power x. Z is acceleration due to gravity, so its dimensional formula is L T inverse of 2 to the power y, and dimensional formula of m is capital M. So in this way, here only T is present, so we can express it in terms of M0, L0, T1. Okay, and in this case here m to the power z, okay, m to the power z, L is x, and here it is y, so x plus of y, and T equal to minus of twice y. Okay, so if you equate the powers in both sides, then you will find that for here in the left hand side m to the power 0, the power of m is 0. Here the power of m is z. So equating both sides we will get, but we will compare the power of both sides, then we will get z equal to 0. Z equal to 0. And for L it is here x plus of y, here 0, so x plus of y equal to 0, or x equal to minus of y, right? And here t equal to 1, the power of t is 1, here power of t is minus of twice y, so minus of twice y is equal to 1, or y equal to minus of half. Since y equal to minus of half, therefore x equal to, hence x equal to what? X equal to minus of half, that is plus half. So we get the values of x, y and z by comparing these two sides. Now if we put x, y, z, the values of x, y, z in this equation, then you will get k L to the power half, z to the power minus of half, and m to the power 0. That means the term mass is not involved in the time period equation, of the simple pendulum. So this expression can be written as L to the power half, that means, and it is z to the power minus half, so it is simply square root of z. So k is equal to square root of L by z. So this is the expression of time period. By using dimensional analysis, we can derive the expression of time period of simple pendulum. Theoretically, it is found that the exact equation of time period of a simple pendulum is t equal to twice pi square root of L by z. Here twice pi, we know that twice pi is a dimensionless quantity, so it is a constant, so it is a dimensionless quantity. So in this way we can express any equation with the help of dimensional analysis. Okay. However, we have learned different formula of dimensions, different formula of dimensions for different physical quantities, but some physical quantities or some parameters have no dimension. They are dimensionless, just like angle. Angle, if we define angle, we consider a circle. O be the center, let R be the radius. So if this radius or this radius vector move to certain point, to this, suppose this R move from this position P1 to P2 in certain time, then it will cross a small distance S, and here the radius vector displaced by some angle, angular displacement is theta. So angle can be expressed by this equation, theta equal to S by R. Here S is the arc length, R is the radius. So both are length. So dimension formula of S is L, and radius, dimension formula of radius is also L. So length will cancel out. So angle is a dimensionless quantity. Similarly, if you want to calculate the dimension of a dimensional formula of refractive index. So refractive index, which you will find in optics, it is nothing but speed of light in vacuum divided by speed of light in medium. Speed of light in medium. Speed of light in vacuum. So speed here, both the physical quantity express the speed. The speed of any object is, dimension formula of speed is LT inverse. So dimension of speed of light in vacuum is LT inverse, and dimension of speed of light in medium is also LT inverse. So these two formula will cancel out. So refractive index is a dimensionless quantity. Some other dimensional quantities are argument of some special functions like trigonometric functions, sine of something, cos of something, or tan of something. So this bracket term should be dimensionless. Sine, cos, tan, cot, sec and cosec, all these trigonometric functions arguments are always dimensionless. Similarly, the exponential functions arguments are also dimensionless. These are dimensionless. This is dimensionless. Or logarithmic function, log of something, it is also dimensionless. So trigonometric functions arguments of trigonometric functions, argument of logarithmic functions, or argument of exponential functions are dimensionless quantities. Let's rewind what we have learned so far. We have learned what is dimension, how physical quantities can be expressed in terms of dimensional formulas, how we can check the consistency of any physical equation, how we can derive any physical equation using dimensional analysis. At this point, I want to stop this lecture. If you like this content, please press the like button. If you want more this kind of content, please subscribe to the channel. You can share the video, and if you have any doubt, please write it down into the comment section. Thank you.